So welcome to this webinar on minimizing complexity of 3D inspections with our new all-in-one vision systems. My name is Jesper Jorgensen, and together with me I have Kai.
Hello, I'm Kai Steuerle. I'm one of the application engineers working for Cognex, and I would say let's give the others a few minutes to have a chance to join. Also, there's a Q&A window section where you can put your own questions if you like. So then we will answer them in post.
All right, so let's get set for it. So today we are going through a few things, and first we will go over the current 3D technology, then some challenges in working with today's 3D vision. What are Cognex bringing to the table as new stuff? Kai will then show a few application examples, and we will finish off with a Q&A session. So the current 3D technology. 3D vision focuses on guiding inspection and gauging applications, guide robotic arms to be able to precisely pick and place parts of on a manufacturing line. Inspect production lines, inspect production to ensure they meet specifications, or perform gauging applications to measure parts, as an example in assembly applications. Kai, can you take us through the common 3D vision technologies here?
Yes, sure. So there are different common 3D vision technologies that are commonly used in the industry. One is passive. So for example, passive stereo or passive multicam applications, where you have multiple cameras generating, let's say, multiple references to reconstruct a 3D image. And then there are the active or so-called structured light technologies, so which is either a stereo camera that uses a pattern projection for generating correspondences and making a more dense point cloud, or the so-called displacement sensor. So here a laser line is being projected into the scene, and the deformation of the line is being used in order to be able to measure the height. And then the system will be moved over your parts or the scene to generate a full 3D point cloud. So then there are also different use cases for 3D vision systems, which is either static, so the parts are not moving. You have a sensor mounted fixed above the part, which is taking a snapshot of the parts, or static or moving. So here you only acquire single lines of profiles and to different jacks onto different positions, or you have it moving. For example, either the sensor that's mounted above a conveyor belt, or the sensor that's mounted on a linear stage that performs a full 3D scan. So then, what are the challenges in today's 3D vision? So basically, we would have to think about how orientation is handled in the system. So is it easy to use, or would you have to calculate Euler angles and transformation matrices by yourself? Then the image quality, of course. If you cannot see the part, or if you cannot get the shape of the part you would like to inspect correctly, then of course it will be hard to perform a certain check. And then, of course, the flexibility of the existing tools. Can I easily tool chain the tools that are there, or do I need to write a lot of code, or do I need to write a lot of code because the image quality is not there? And if I would like to have this running on an embedded device, I would have to think about the processing power that will be needed by adjusting the tools code-wise.
Yeah, so what's new in Cognex 3D? So here we have, to address these challenges, we, oh, sorry. Let's see if it starts. To address these challenges, we developed the new 3D smart camera to make 3D applications more accessible. It has a small form factor. It has rugged industrial design with high IP rating. It's a built-in FPGA and state-of-the-art laser imaging technology. It even has industrial Ethernet directly on board. So the Insight 3D-L4000 is running a multi-core processor, which allows the system to solve applications without the need of a controller or industrial PC. Thus enabling opportunities to a broader range of 3D applications throughout the industries. This easy-to-use smart camera is based on a well-known Insight spreadsheet environment and uses a broad range of true 3D vision tools on a point cloud image. It's making 3D as easy as 2D. So thanks to a patented laser imaging technology and advanced optics, we provide you with the highest quality image quality and speckle-free 3D point cloud images. The tool performance is highest performing and has the broadest range on the market. And lastly, the ease of use is achieved by using the Insight spreadsheet setup. You don't have to have any programming skills. It's not mandatory. If you want to do specific stuff, you are able to do that as well, but it's not mandatory. How can we use it? It's it's a smart camera. So what you do, everything is embedded in one device, and what you need is you mount the camera, you connect the Ethernet cable either directly to your PC or to the network you're having. Then you plug the power cable, and you are actually ready to start working with the system. So Kai, can you take us through the visualization here?
Yeah, right. So basically, there are several things you would have to have a look for when it comes to the ease of use of 3D systems. So step one is visualization. So basically, 16-bit height maps, so this is how height is represented in a 3D system, are pretty hard to read to the human eye. So if you have a look on the image to the right, you can see the washers that are in between the screws and the part quite barely with your eye. And also the measurements are impacted by part positioning and orientation. So for example, if you have a higher higher Y resolution than the X resolution, or if the part is slanted a bit. So, and to cope for this, we have a 3D point cloud view that enables you to have a much nicer view on the part itself and to easily and directly see what you're doing. So basically, if you're adjusting regions or moving your tools onto several parts that have to be inspected on your sample part, you can easily navigate through the point cloud without having to struggle on reading height maps. And then, of course, Jesper was talking about the speckle-free laser. And here we have a patented optics. So basically, we have no speckles due to aliasing. And what does it mean? So if such a displacement sensor is acquiring an image, what you see is a laser line that's being projected onto the scene, and a camera that's looking at a certain angle onto that laser line. So the camera sees a deformation based on the profile in the image. And this deformation is used to calculate the height. But then there could be some dark and bright spots caused by interference, either constructive or destructive, of the coherent laser light itself that will cause a failure in the height. And to cope with this, we have invented our patented speckle-free laser that produces a more homogeneous laser line. So here we even have a much higher sub-pixel accuracy to be able to process details much better. So basically, this requires a more clear and crisp 3D image that will help you with your 3D inspections. And here on the right, you can see an image that's being acquired by the 3D L4000. Especially if you have a look in detail, you can see that the laser line itself is pretty homogeneous on the sample part itself. So, regarding tools, we have a broad spectrum of 3D vision tools that are available, and they're designed to solve the most real-world application tasks. So you can easily tool chain those tools into each other, and there are also 2D tools available. So next to the 3D scan, you will also get a 2D image where you can perform 2D inspections. So for example, inspections that require to have the color on the part itself or the gray values. And you can do 3D inspection in one and the same scan at the same time. Then we could question ourselves, so how do I set it up? So if I have this device, if I have it freshly unpacked, how do I set it up? How do I use it? So what we have is our Insight Vision Suite, which has a spreadsheet environment. So basically, you have a spreadsheet in the center where you can drag and drop 3D and 2D vision tools from the right toolbox into your spreadsheet. You have a 3D display on the right where you can adjust your 3D regions, and you have a 2D display on the left where you can adjust your 2D regions. And in addition, you also have a visual feedback on both images. Then if you develop such an application, it would be nice to have the tools easy to use. So how did we do that? Basically, we've enriched the spreadsheet with our 3D vision tools that you can just drag and drop to a certain cell. If you do a double click onto a 3D vision tool, a property sheet will open. And you can directly set references for other vision tools, image sources, etc., or parameters based on other cells. So here, it's easy to use due to the point-and-click functionality. So you can also set regions directly by drag and drop and rotating it with your mouse, and no programming skills are needed. In case you would still like to program, we also provide you with a scripting cell.
All right. So what if you then face some issues and you really don't know how to work with that certain tool you're working with, Kai? How do you seek help?
Yeah. So basically, every tool itself has a so-called property sheet, and this property sheet has an embedded help. Either for the parameter you have currently selected, you will have a quick help on the lowest section of the property sheet. Or if you would like to have an extended help, so for example, theory on how to use this tool, you will have this question mark in the upper right title bar of the spreadsheet where you can just directly click and an online help will open and show you the use cases and how to set the tool up in detail.
Okay, so then Kai, can you try to take us through some application examples?
Yes, sure. So I've chosen 4 application examples. Here are some application examples that do defect checks. So those are the ones on top. So for example, a brake pad inspection or a battery cell inspection. Then we have a presence-absence inspection for packaging and also a presence-absence inspection for electronics. So here for the defect inspection, basically this is a battery, but it could be any cylindrical part. We have first a cylinder fit that finds the part in a 3D space, and then we're going to detect basically a deformation on the outer cylindrical wall. So the question is, how is this done? So, and basically what you can see right here is the spreadsheet environment with a defect on the 3D sample part that has already been detected, and also the defect marked on the 2D image as well. So how is this done? First, we have a cylinder extractor that finds and detects a cylinder in 3D, or finds and detects a cylindrical part in 3D. And this will be used as a 3D reference for our 3D blob tool. The 3D blob tool finds any deformation based on a reference. And here for the cylindrical part has a certain damage that is found and can be classified by volume, size, height, and position. The next example, we have an easy absence-presence application for packaging. So here you can see a shoebox that is first being localized in the 3D environment, and then inside the shoebox, the shoes are being inspected. So basically, what you do first is insert a tool that finds the box. Then, based on that, you have a tool that computes on the box, on the location of the box, 3D bounding box. Within, you can search for your parts. And on that, if you just do not want to check only for the volume, you could also check for the height distribution within the box to ensure that there are boots inside and not different parts. And then, of course, we said that our tools are prepared for many real-world applications. So here, for example, you do not have to write your own code to sort the things that you have found within the box. So, for example, you could sort by center of mass or positioning based on X, Y, and Z coordinates. And then we have an application regarding presence, absence, and also placement for electrical parts. So what you can see right here are electrical components on a tray. And the target application is to find whether a component is missing or a component has a wrong orientation for the adjacent process, so that those components can be soldered in place correctly. Then we have a defect detection. So here we're inspecting for dents or other defects on a brake pad. So this is done by just having a plane extractor tool that finds a plane onto the top of the brake pad, and then we're looking for material that's missing or material that's excessive on the part itself. And we're classifying those defects by volume and size. In addition, you can also perform a check on the edges. So you can also measure the gap in between those brake pads as well.
So, Kai, what kind of resolution do I need?
Yeah, there's a common rule of thumb. So basically, we would recommend roughly 10x for measurement applications and 5x for absence and presence applications. And also, you would have to keep in mind that the resolution in Z is not always the same as the resolution in X or in Y. So, for example, this depends on how close your sample part is being placed next to your sensor and how fine the encoder resolution of your conveyor or linear stage is. And you should also keep in mind that resolution is not the same as image quality. So your sensor has to be able to see the part to be able to inspect it. So Jesper, what are the industries we're targeting?
Yeah, so we've shown some examples of the industries today to give you an idea on how you can benefit from using the new Insight 3D Smart Camera in your industry. I would urge you to get in contact with your local contact and challenge us with any applications you have, whether it's volume measurement of a salmon fillet, as one of the examples here shown, or if you are missing a shoe, then get in contact with us and we'll take a look at it. So we can definitely say that we are ready for any industry, if it's automotive, pharma, or food, what it is. It's we will be ready for that. We will now switch to the Q&A session. And we have had a lot of questions coming in. So we'll